So hi, I'm here to talk about ZFS on OSB, where I will explain all the concepts around and how it was to get ZFS working on the platform. So I will not explain and show step by step how to get ZFS working on the platform, as it will take a lot of time, and that will not be done within a 30 minutes presentation. So I will show some of the steps needed to get ZFS working. And I think I should really mention, should really explain that OSB is a completely new operating system written from scratch to work on cloud workloads. I'm going to explain it a little further in a couple of minutes, but so that's basically the introduction. So before I introduce myself, I would like to say that I'm really glad to be here for this presentation in OpenZFS conference. I'm Raphael Carvalho. I come from Brazil. I work for Cloudius systems integration of OSB. So in Cloudius, OSB specifically, I have been working with ZFS and all the technology around block devices and file systems as well. So right there, I work on ZFS and virtual file systems as well, and that means RAMFS, dev file system, and all the other file systems as well. So our version of ZFS was ported from previous zip, and that's basically. So let me go to the next slide. So here I go to explain OSB. So as I said, it's a completely new operating system designed for the modern cloud era, and that allowed us to cut off a lot of different layers of complexity. And OSB takes advantage of the fact that on modern cloud era, you can run single application for a virtual machine, and that means that you have an operating system with a single process. So we can cut off layers of complexity, abstraction of where you have a single address space, and one of the few components that we reused was ZFS. So ZFS is used as our default disk-based file system. So ZFS, the unique file system that we use on OSB for the purpose of writing the disk, communicating to the disk and turning memory. So as I stated here, ZFS is in the process of getting stable. So we started getting ZFS to work on OSB in the past year. That was when we started developing OSB. And as OSB was licensed under ESB, that allowed us to integrate ZFS within our core, unlike ZFS in Linux, for example. So generally speaking, OSB follows Linux API, and that allowed us, as I stated right below, to create a dev file system where the lead ZFS rely on the ZFS device entry to communication, where that ZFS basically is a device that communicates with the ZFS port. So you have the ZFS device communicating with the lead ZFS, and you have the comments on top of that for creating a pool or removing a pool, and etc. And that's basically what OSB is. So a simple operating system for running cloud workloads. So in this slide, I would like to explain why we decided to use ZFS, and that should be very clear. So OSB was designed with effortless management capability in mind, where you wouldn't take a lot of effort to manage the operating system. So you would just launch your instance, and you would not take a lot of time to manage and, for example, tuning your operating system, all the layers for your specific workload. So that's what we are trying to achieve with OSB specifically. Create something simple, specific for your workload, for your cloud deployment, where it will not take a lot of effort. And ZFS provides exactly that, where you have snapshots, reliability, efficiency, immense capacity, and it doesn't take a lot of effort to get ZFS working for your workload. And it adjusts itself for a variety of workloads. And that's what we choose to use ZFS, and we're taking a lot of advantage for that specifically. So that's the milestone. So as you can see, we created OSB in the beginning of the past year, and we started, at that time we were using RAMFS, which is a file system that just ends up writing data to exist. So it's a memory-based file system. And so as we need a disk-based file system, so yes, we use Fidel, it's compatible with the BSD license, and that allowed us to choose ZFS. We also had the option of using UFS, which is definitely a great file system, but ZFS is much better for our model of deploying things in the cloud. So as you can see, we got ZFS to mount in the middle of that year, of the past year, and 2 months later we got the read and write support from ZFS working full within OSB. And that's great because Cassandra, for example, sometimes need additional file system to take maximum advantage. So you can, with ZFS tools, it's much better in that matter, where with a single command you can create a new file system, and so it's much better in that matter for a lot of workloads, for cloud deployment, for storage deployment. ZFS is much better. So that's basically why we decided to use ZFS, and that's the milestone of ZFS specific. I will not go to the other flows. So here I go with the steps, not all the steps of first, but some of the steps needed to get ZFS working in the platform. So of course we started with the ZPL. To get ZFS compiled in a new platform, you have to support Solaris code as well, as ZFS relies on a lot of code from Solaris. So as I mentioned earlier, our version of ZFS was ported from FreeBSD. So we had to take a lot of code from FreeBSD and integrate into our kernel. So the first entry here is ZPL, which is the layer that communicates with the digital file system layer. And that means the basic function for a file system, and that means write, read, and a lot of sync, fsync, and so on. So that was the first thing that we had to do, adapt to ZPL, which is the ZFS POSIX Layer, as you can see here, to work with OSB. I should really mention that OSB uses the FreeBSD ZFS layer, but it's modified specifically for OSB. So we had also to integrate ZFS I/O layer with the block I/O layer of OSB. And the next step was to integrate the adjustable replacement cache, which is the ZFS primary cache reclaiming, which is, for example, because the main purpose of having an operating system is to run applications. So if ARC adjustable replacement cache is using a lot of memory, they needed to give that memory back to the operating system to give it for the applications. So upon memory pressure, the operating system will go to the ARC reclaim and say, oh, I need X amount of memory to be given back to the application. So it would go to ARC reclaiming, which was integrated into our reclaiming infrastructure, where many subsystems of the operating system have its own reclaiming function. And ARC adjustable replacement cache provides that, and so we have to get that function integrated into our reclaiming infrastructure. So that was the next step. So as I stated, also dependent code integration, which we get from FreeBSD, so we have to port a lot of that code, which ensured FreeBSD had to port a lot of Solaris code. So the next step, the final one to get ZFS actually working, where you would see some of the results, was to to integrate ZFS import and mount integrated into the boot process. So during the boot process, we will have to import the root pool and so mount ZFS root file system afterwards. I'm not sure if I mentioned, but ZFS is our native file system, and so we actually have to start with the RAM file system, where you have the RAM file system for helping the boot process. And afterwards, you go with the ZFS and use a system code specific for that, where you will switch from RAMFS to ZFS, and that happens in the middle of the boot process. So here is the virtual file system layer, and I'm going to explain it a little bit, although I have explained the essential in the previous slide. So virtual file system layer is the layer from the operating system that allows many file systems to coexist and communicate. For example, in the same system you could have X4 and ZFS and other file systems of your choice. So the virtual file system layer is where the file system consumers go to. I want to write to such a file from ZFS. So you have the file system namespace. So you have root slash the name of the file, the directory, and so on. So virtual file system layer is basically the layer that allows all the file systems to coexist, where you can call a file from one file system to another. So that's basically what we have to work on ZFS specifically, because as I said, our VFS layer changed. Our VFS layer was ported from FreeBSD, but we had to change it as well. So we had to go to ZPL and modify it to work with our VFS, but it didn't take a lot of change. We wanted to keep the ZPL as it was originally, and we are trying to get in sync with the FreeBSD so that it would be easier for us to pull changes from the FreeBSD, new changes from OpenZFS as well. So let me go to the next slide. ARC reclaim integration, I explained as well. So the orange figure, you can see that there is the general reclaimer from the OS, which is the infrastructure itself. And you can see on the right side of the slide that is the ARC reclaimer, and right below the other reclaims that I also said. So that's the change we have done within our ZFS version. So ZFS POSIX Layer. So we have changed some of the ARC reclaim policies as well to inform the operating system how much memory was reclaimed. So the current version of ARC reclaim function doesn't provide how much memory was reclaimed. So that was actually needed specifically for our reclaim infrastructure, our reclaim policy. And one change that we have done that is very interesting, and we would like to share it with the other platforms as well, is something called ARC buffer sharing. That when you do a memory mapping, you go to ARC and you don't need to duplicate that buffer. So you can get that ARC buffer and map it directly to the process address space. So if I'm not mistaken this correctly, in ZFS on Linux, you will get our ARC buffer and duplicate it and map it to the address space where you have it, because it's not well integrated into the page cache on Linux itself. So as we have total control of OSB, so we could change our page cache totally to be well integrated with ARC. That's a default replacement cache. So one change that I was working on it myself was to allow the ZFS boot pool to boot with more than one dev. So if I'm not mistaken, you cannot have the root pool with more than one dev during the import. So I just have to go to the SPA, which is the storage pool locator module from ZFS, and there is a function specifically for importing the root pool. So I have to change it to be aware of all the other VDAPs that is inside the same pool. So it didn't take a lot of change, but it was nice, and I would like to share that with the other platforms as well. So let me go here. So that basically explains how our ZFS ARC buffer sharing works. So you have here the centralized function for memory map, where the application will issue an map code, and that I wanted to map the range from a file into the address space, so you go with mmap. And in ZFS, on Linux, you would, the operating system itself would go to ZFS ARC and get those buffers and copy them and map into the address space. So you would end up with duplicated buffers into the address space. With ZFS, once again, on the other hand, you can go to ZFS ARC, grab those buffers with respect to the range that we're trying to map, and you will get those ARC buffers, and you will, internally speaking, you will get the DMU buffer, you will get the ARC buffer out of the DMU buffer, and we integrated, we exported OSB function to map the ARC buffer directly to the address space. But I should really say that it's limited to read by the time being. So upon write, you will end up with a copyright on that read-only pages. So by the time being, we have to get those ARC buffers and map it into the address space with the read-on flag. So in the next slide, I'm going to explain that. So let me say that you will have the address space with read-only pages. So once in the time that you do write for that page that were marked in the past with read-on flag, the operating system would get into a page flow and will have to duplicate those ARC buffers. So from that time on, we will not be mapping those ARC buffers anymore. So we have a specialized write page cache, that's how we call it, that hold the copy ARC buffers. So from that time on, we would be exactly like ZFS Linux that has the ARC buffers duplicated into the address space. So we actually have a plan for the future where you could write directly into the ARC buffers that would map into the address space, but that would take a lot more of effort. So by the time being, we just have that feature for reads. So on write, as I mentioned already, you would do a couple writes. So that's basically the resume of this feature. So right here is where I'm going to say the plan for the future, where I already mentioned earlier, is to get in sync with the other platforms, especially FreeBSD. That's where we get ZFS from. And hopefully we will share our modifications with the other platforms as well. Of course, those that would be valuable to them. I was talking to Matt yesterday, and I would like to, and it would be nice if I had brought a benchmark, but it was not possible, so I'm sorry. But in our benchmark, we noticed that we are in the same level as ZFS on the other platforms. But when it goes to the cloud, we can perform a little better, because we can batch writes, for example. So the block IO device driver was specifically designed for EC2 or EC2 from Amazon, for those who don't know, or even Google Compute Engine as well. So our operating system OSB was totally molded around the cloud environment. So that's basically what I have to say for today, and I hope you like it. And if you have any questions, it will be well. Please.
Yeah, so it sounds like what you're trying to do is somewhat
Yes. Yes. OSB was based, is based a way of doing Docker, but in other ways. So we are trying to achieve the same, but going through other methods. So OSB is basically trying to provide something that's well isolated. So when you have a single process, you don't need to care about isolation anymore, given that you have a single process. So when the scheduler wakes up, you don't need to do all that context switch anymore between address spaces, given that address space is supposed to hold a single process. So if you, of course, you can have many threads within OSB. So, but as threads share the same address space in context switch, you don't have to go out without that changes anymore. So everything is so much simpler, and OSB was designed to run on top of a hypervisor, so it was well integrated with that, and that's basically how OSB was supposed to be run.
So the idea is a very secure environment. It's a very secure container.
Yes, it's a sort of lightweight container, but it's an operating system itself. So it's basically like Docker, but we're trying to go to the other path to achieve the same. So we're still in the process of measuring results, and we'll get good results. For example, Memcache can run even faster than only host, as we have designed our own TCP stack from scratch, specifically for this problem.
So as a user, if I want to compare zones, I'm just trying to understand, like, as a user, strictly not knowing anything else. Just if I know I've got zones, I'm able to
Yes, OSB works it's operating system that's supposed to run on top of virtual machines. So if you want to run OSB, you will go to the cloud, upload the image, and so it's not like Docker when you have all those namespaces on all those features for isolated processes within its own namespace. So with OSB specifically, it's pretty much like when you're using a gas operating system on the cloud. So it's a short explanation. So it was actually, well, that's actually a good question. I'm not sure. But integrating the ARC into the address space and ZPL and get Solaris code integrated was pretty hard actually. So that was one of the hardest part in the project. Actually, we take into account that our buffer is in granularity of 128 kilobytes, so you can divide that by the size of the page size, and so you can map. You can grab the ARC buffer and map directly into the page, into that display source. Yes, in mind. So in the page test itself, we grab those buffers and we try. Actually, for example, when you do a neural net, we look at the range that has an element. So we get as many pages as we can. So if there is, we try not to reduce the neural footprint and get it working well. So that's based about the neural net. I actually don't remember all the details that have been trying to do. That's basically how it works. Oh, in that case, we rely on the case that we will copy the buffer. So in that case, so you're asking about the file system, right? So in that case, I'm not sure if we handle that specifically. So we have more generic implementation for that. Alright, so we put the